Hello students, so we are going to have a discussions on the Lorentz force. Many of you face a problem to find out the direction of the magnetic force experienced by the charged particle. Not only in this case, or whenever we talk about the current carrying conductor also placed in the magnetic field, how to find out the direction of force. Not only in the class 12 students, class 10 students, wherever they start, they learn it from the Fleming's left hand rule, right? But we are not going to use the Fleming's left hand rule. We are going to use a different type of rule, and that rule is going to be very much easy and helpful for everybody to find out the direction of the magnetic force experienced by a charged particle whenever it is placed in a magnetic field, whenever it is moving in a magnetic field, right? So the expression of the Lorentz force, you know, that is written as Fm, that is Q into, I'm not talking about any kind of electric field is applied, I'm only talking about the magnetic field is applied here. Q into V cross B vector. There is a cross product. This is also a vector. So this is the force experienced on the charged particle, taking that charged particle as positive right now. Okay, because for negative charged particle, the force is going to be exactly opposite what happens in case of positive charged particle. This is velocity vector of the charged particle. This is the magnetic field vector, right? Suppose we take a charged particle Q, which is entering the magnetic field with some velocity V. So question is, in what direction the charged particle is going to shift, in what direction the trajectory of the charged particle is going to be. That means in what direction the force of the charged particle will be. So to find out that, now this cross sign signifies that the magnetic field is into the plane of paper, right? So you also have to learn this symbol, that cross indicates into the paper, because this is a three-dimensional case. We cannot show you into the paper or out of the paper. We have to give it by the sign conventions. Up and down in the board we can show you always by giving some arrows, but into the paper, out of the paper, it is written always by the cross and dot sign. So this dot sign represented as out of plane, and this is into the plane. Now in this particular case, you can understand the cross sign signifies the magnetic field is inside into the plane of paper. The charged particle is going towards this direction. We are not going to use the Fleming's left hand rule, by the way. We are going to use the palm rule, right hand palm rule, a very easy tool to find out. You may not use the Fleming's left hand rule, but the same result you are going to get whatever you get in the Fleming's left hand rule. So in the palm rule, you can understand, if I hold my palm like this, this is the right hand, not my left hand, right? This is the right hand. This finger, this thumb represents what? This thumb represents the direction of the charged particle, right? The direction of the movement of the charged particle, the velocity vector. And these four fingers, how will you should not confuse between the V and B vector. B always you represent by some parallel lines. The magnetic field vector, you always represent some parallel lines, 4 lines, understand by this. So these are going to be represented by the magnetic field lines, magnetic field direction. This is your velocity vector. And V and B are in the same plane, and you know, whenever you use a cross product, the result of the cross product is always perpendicular to the direction of the plane containing V and B vector. So these two vectors, and its result is the force. So force is always going to be perpendicular. This Fm is always perpendicular to both V vector and this magnetic field vector. So how you can get the direction of force right now? So this is your V vector, and B vector is into the plane of paper. Take your right palm. All of you take the right palm. Okay, so magnetic field represented by these 4 fingers. So into the plane of paper, we will take it inside the board. We will point our fingers inside the board, and we will point the thumb into the direction of the velocity vector of the charged particle. That means towards my right side. So this is my right side. I hope you can understand this fact. Now see the front face. You can take some pencil over here, not like this. You have to take the pencil like this always towards, just like you do some, you give some worship to somebody like this. Okay, so magnetic field vector, velocity vector, you can understand my right, the front face of the palm is represented in the upward direction. That means the force is going to be in the upward direction in this case. So velocity vector, magnetic field vector in the same plane, the force is perpendicular to both the velocity and the magnetic field vector. So it will experience a force in the upward direction. So the moment it experiences force in the upward direction, instead of going straight, it will take a curved path like this. The moment it goes along this direction, you can understand, whenever you take a kind of as it is going to move in the circular path, the direction of the tangent gives the direction of the velocity vector right now. So velocity direction changes. So velocity is direction, magnetic field vector, force vector. The force will come along this direction. I hope everybody can understand. So it's kind of centripetal force the charged particle is going to encounter every time it moves forward. So it will have a kind of circular path. So this is how the importance of right hand palm rule we discuss. Okay, so don't use left hand Fleming's left hand rule. Use the right hand palm rule to get the direction of the magnetic force easily. Thank you.